presentation actually. It's
These are
working,
point.
I think.
Huh? No, it's working for first few slides. Oh, now it's working. I don't know. Anyway, yeah. Okay. So anyway, we'll start with this linear vectors. Okay. So first thing is that you already know what vectors are like in 3D. Okay. So our idea is just briefly recap these 3D vectors in 3D. They are also linear vectors, and then we'll extend that to ND. Is it okay? Okay. So in 3D real space, you define a vector with this type of arrow, right? It is like a coordinate system, right? A point in 3D. Okay. So these are called unit vectors, and they are mutually orthogonal or orthonormal, right? So how do you define it for ND space, n-dimensional space? We call it Hilbert space, but anyway, we will not get into that. But how do you define it? So we'll do almost similar thing, right? So the way we have, so we need a couple of things. We need coefficients and we need some basis. Since you have done crystal structure, you know the essence of basis, right? So we need the basis. So how we define basis vector, we'll just figure it out in a moment. But do you understand? We need basis vectors, and there are some properties. So for 3D, it is very easy, x, y, and z. Okay, with the help of these vectors, you can identify any point in 3D. Same thing we need to do for the ND. Is it okay? So note that the style, the writing style is now different, the notation. Okay. So here we had this arrow and now we have this bracket. Is this fine? Just the notation difference and nothing else. And whenever we have this coefficient, we can write or express it in terms of row vectors. Here it was 3 cross 1, right? Here it will be n cross 1. Is it okay? Yeah. So when I'm saying is a bracket, so we have two parts, bra and kit. So we call it kit, this symbol. Is it okay? Just the same thing here. You previously used to have this arrow. Now I'm just doing it because later you'll see it will make your life very easy, and you have to think everything in terms of matrix. So in matrix, what you have? You have row vectors. You call it vector, right? You have row vector, column vectors. So this is row vector, right? Column vector. Okay, fine. This column vector n cross 1, right? Oh, okay. So yeah. So that's point number 1. But we need to understand how to define basis. Okay. Okay. Next, what are other things you learned? Magnitude. How do you find magnitude in 3D? Do you agree with this? Modulus of this, and square root. But if it is a space, 3D real space, so we don't have any complex numbers, right? That's why you sometimes C1 square, C2 square. But you have also worked in complex print, right? Say 2 plus 3i. How do you find modulus of that? With this, okay? Then how do you do the same for ND space? If I have n-dimensional vector, where this coefficient can also be complex. Now you have to liberate yourself. We are expanding. Okay, it can be real complex combination of many different things. Okay, do you think this is the right approach? So we have this is a column vector. If I transpose, then we get this row vector. And yes, complex conjugate, right? Then we get this, and I hope you know how to do matrix multiplication. So eventually you get C1 square. So this is 1 cross n, and this is n cross 1. Final product will be 1 cross 1, right? A magnitude. Do you agree? Very easy, right? That's all. So now, this week we are calling kit. When we have complex conjugate of that, we call it bra, so that it is bracket. Is it okay? Simple? Okay. Fine? Okay. So now, if you want to take scalar product, so here previously you have seen scalar products, right? You find angle between two vectors, this and that. Is this the way you used to do? Right? So same stuff, okay, we can also do it for here. So now instead of doing this, we can have n by n. This is a good representation. Do you agree or not? So we have this column vector and we have this complex conjugated row vector. Do you agree or not? Okay. So now, so this is coming from this side, right? Ket. Remember here? And this side is like bra. Okay, I just put them together. So when I put them together, you should understand when I am using this symbol, it means this. Is it okay? Very simple, right? Just think. The only thing you need to think is this. Okay, one is row vector, another is column vector. And when you put these guys together close by, so you have close bracket. This part is called bra, this is called ket. That's all. These are Dirac's notation. Okay, to simplify your life. Really, you will. The more you spend time here, you see that it will really help you. Is it okay? Simple, clear? Okay. Now what else? Cross product is different. Okay. We'll discuss it later. Huh? Huh? That's a difference. So anyway, important question is still missing. How to define this U1 and U2, right? We are saying that this is n-dimensional basis vector. If we know, then we are almost set. Later on, you can do many other things to understand, but these are very essential, right? We just consider now the most essential ones. Okay. So here in 3D coordinate system, you know this x, y, z, we call it orthonormal, right? Orthonormal meaning if I take a dot product or whatever scalar product x dot x, it becomes 1. If it is x dot y, it is 0, right? Other combination, it is 0. And in 3D, we relate this to angle between them. If in 3D, right? And we call it 90 degree. So essentially what we are doing, we are saying we are doing some operation between two vectors and that gives you 0. And somehow in case of 3D, that is 3D or 2D, it is 90 degree angle. So we just need to do same thing for this. So this is this one, right? So this operation, whenever this operation is 0, we call it orthogonal. Do you agree or not? Agreed? So now this operation should be 0 for ND. Then it will be orthogonal. And this is the magnitude. If it becomes 1, this is unit vector. Orthogonal plus unity is orthonormal. Meaning this. Do you agree or not? In 3D that you are used to doing. Okay. So now you need to just calculate this. Calculate this. We call it inner product. Okay. You need to calculate this inner product. Okay. Now how will you know whether they are orthogonal or not? Vectors are given. You know how to do matrix multiplication. Do it and check. Is it okay?
Sir, in n dimension we can also talk about angles like
No, that's why here, yes, now you need to think beyond that. The essence is the important thing is not the angle. Important thing is this operation. That eventually turns out to be angle for your ease in 2D or in 3D. Maybe there are aliens who can see or visualize in-dimensional thing. We may not be. Okay? But definitely we can do maths. We can do this operation. Is it okay? Clear? Okay? So now we are almost there. So this is how you can define basis vectors. Check for this. If it is satisfied, then you have the basis vectors. Note that these basis vectors are always linearly independent. Okay, here I may give some homework problem how to figure out whether it is linearly dependent or not. I don't want to spend much time there. Here the matrices and this row column vectors, whatever we had, they are linearly independent. I'll give some homework problem where you see that which one is linearly dependent, which one is not. Okay, you'll solve for that. Okay. And another thing, whatever linear operations you do, for example, addition, but anyway, in signal systems, you know, right, how to define linear system. Okay. Anyway, you know what is linear and non-linear things. So whatever operations you do, multiplication, addition, subtraction of a vector with another vector or scalar, So it should belong to that same vector space. The final product will be a vector. So that previously we didn't take care that much. For example, if I have a vector v, if I multiply that with 0, 0 is a scalar, right? What do you get? This is a 0 vector because we had a vector and we multiplied with a scalar. End product must be a vector. Yes, we call it null vector. Similarly, you can subtract, right? I have one vector here, another vector just opposite to that. If I sum them up, I should get 0 vector, not 0. Okay. Okay. Yeah. So that's all actually. That's part number 1 all. Is it okay? So, okay. So these are very basics of linear vectors in linear vector space. There is one more thing. Okay. So we are now talking about vectors. What is remaining? You tell me. Huh? Someone said? Tensor. Right? So this is a row matrix or column matrix. Okay. Now what we have, sorry, row vector or column vector matrix. Okay. So 2 cross 2, 3 cross 3, n cross n. Okay. Okay. So before discussing that, yeah, so I'm calling it operator. Very soon you will understand, maybe in like 5 minutes, what operation does. Okay. So can you tell me what do you get here? Do it and let me know in 2 minutes. Very simple. You get a vector, right? So this is a matrix 2 cross 2 or n cross n. So this is, I forget, this is column vector n cross 1, right? So you are saying this. So you get another vector. So when an operator operates on a vector, that vector can be transformed to another vector. It cannot be scalar. Okay. Yeah, that's the role of operator. It is doing this operation. Simple matrix multiplication, right? Now you will actually understand. So previously you started matrix, right? Now you will understand. So I have probably given a lot of insight of Fourier series and Fourier transform, right? Now you will understand this linear vectors and matrices, where they are actually used. Okay, or the power of mathematics. Okay, now you need to relate. Maths fine. Again, you need to have the connection, real life connection. An example of operator. Okay, whatever you can visualize. Let's take a simple one. Okay, let's take a vector in 3D. Anyway, if I can take it in 3D, you can take in ND. It's not an issue, but in 3D you can visualize. Suppose my vector is oriented along x direction, and I have an operator that, when that is operating on this vector, it just rotates it by 90 degrees. Okay, I can give a nice name, a cute name, operator. 90 rotational operator. Okay, this is what I mean. I have a vector. Now all the vectors will define in this form. Is it okay? The column vector. Okay, only coefficients. We have this 1 0 meaning along x is 1, along y is 0. I just dropped the z term. This is one of the vectors, and we have this 90 degree. We have an operator that just rotates it by 90 degree, meaning you are actually doing it. Okay, let's assume you are just operating, you are just rotating it by 90 degree. You are doing it, so this is an operation. Okay, do you agree? Now mathematically, how do you define the matrix elements of an operator? That you can define. Okay, so here you will see that this matrix elements will be cos phi, sin phi minus sin phi, stuff like that. That will be your homework problem. But are you getting the point? So this is like, here you started with that, and here this is what you have. Okay, and in between we have this matrix, because so here we have this 2 cross 1 column vector. If I have matrix, then If I multiply this with that, then we get another vector. Okay, that means operators, whatever we are saying, is just nothing but matrix. Do you agree or not? If you want to know operators, you want to know the matrix elements. That's all. Sometimes it might happen that I will give you matrix elements and you can do the operation. Or it could be the other way around. I can give you like the outcome of the operation. You can figure out what will the matrix elements be. For example, how you define rotational operator in 2D or in 3D. Okay, for example, you take a vector and you rotate by theta and phi, define the matrix elements. That will be the homework problem. Okay, let's not do that in class. It might take some time. But you got the point or not? That's the key. Is it clear? Okay. Now let's take another example. Okay, let's take the same operator omega. Now let's take this vector. Do this matrix multiplication and let me know what you get. One minus one with so our vector was v, which is 1 minus 1. And after this operation, again it is 1 minus 1 with a scalar. Right? So this is slightly different from that. So these are the two possible cases. Do you understand? So here what is happening? So you are getting this scalar. So this is called eigenvalue. So this scalar, whatever we have, these are called eigenvalues. And whatever vector we have, these are known as eigenvectors of this matrix. Okay, so I can write, yeah, this is one just a way to you can visualize. Let's take this vector, okay, 1 1. Now I have a scaling operator. Okay, I make it larger just by factor of 2. So it becomes 1 1 multiplied by factor of 2, right? So do you understand the difference between these two processes? Okay. Okay, so in general, it is not that all the time it will happen, but in some cases, okay, we can have an operator, that operator perhaps working on a vector v, and in that case, we can still get that vector with a scalar multiplied by the scalar. In that case, we call it eigenvalue, and we call this eigenvector. Now you will know, right? So in 10 plus 2 or maybe even before that, right? You have done a lot of this eigenvalues, eigenvectors. Okay, just recap for you. Okay. Now if I give you a matrix, can you find these eigenvalues on vectors? Let's take this matrix, and this is how you can find eigenvalues, right? You take the determinant and solve for it. If it is 2 by 2 matrix, you can have two different, not different, I mean, you can have two eigenvalues. If it is n cross n, you can have n eigenvalues and eigenvectors. Right? Just do it quickly. What do you get for what eigenvalues do you get? They're simple, right? 2 cross 2. Finding eigenvalues that you have done in 10 plus 2, then in your bachelor's. Okay, minus 3 minus 1. Okay, something like this, right? Anyway, if you do it, then you'll, okay, fine, yeah. Okay, fine. This is what you have already, this is just brush up. Okay, but the thing is, we'll connect these two quantum mechanics. That is the most fun part. And then you will understand what were these things, eigenvalues, eigenvectors, why we started that for so many years. Okay, what's our next step? Finding eigenvectors. Find eigenvectors. How do you find? You do it like this, okay? Take this, okay, and have this coefficient. Finding eigenvectors meaning you need to find these coefficients, right? We have it with this coefficient, and it will return this with some eigenvalue. So we have 2, 3 and 1. So we are doing it for 3. If it is 3, So there are two equations and two unknowns. You can solve for it. Is it okay? Two equations, two unknowns. You can solve for it. Yeah, and this is a relation. Okay. Now you can feel free to have any value. For simplicity, we can take 1, 1. If you take 1, 1, this is one of the eigenvectors. Sometimes in quantum mechanics or anyway, we normalize, right? Then say you take 1 by root over 2 out. It's not an issue. You can take 2, 2, 3, 3. Okay. The reason is that I mean in crystal structure we said that these basis vectors are not unique. You can have many. Okay, they're all fine. Okay, now tell me what will be the eigenvector for this eigenvalue 1. Do the same. You again do it and let me know what are you getting. I'm pretty sure even in GATE such simple questions don't come. Questions are much tricky, which you have done. Very simple question like this. 1 minus 1. Very good. Okay, you're doing something like this. Okay, so what is the overall summary? What we learned from this? We see that okay, we have linear vectors which are which are column vectors. I call it Ket. You can take complex conjugate. I call it Bra. Okay, so we have seen inner product, which is just the multiplication of these two vectors. Then we have seen operators, which are n cross n matrices. Okay, and now, so if we have an operator and when it is operated on a vector, we can have the same vector with a scalar quantity multiplied, or we can have a vector. There are two possibilities. So when it falls to this category, then we call it eigenvalue problem. Then you can find eigenvalues and eigenvectors. Okay, and this is one of the examples. So it is not that always you will have these eigenvalues, even if it's satisfied, you will have these eigenvalues and eigenvectors. The reason is, or if you have these eigenvalues, actually you can put this, and there are ways, I'm not doing it, you can diagonalize the matrix, okay? But it is not that, I mean, it's not that always you can do it. That after that you have to check whether they are linearly independent or not. Okay, but anyway, I'm skipping it for the time being. Okay, but overall you got the idea, right? Okay, now any questions? No question. Okay, we have 20 minutes. Okay, for quantum mechanics, very basics. Okay, so previously in quantum mechanics we have seen, I mean, the emergence of quantum mechanics, the birth of quantum mechanics, the need of quantum mechanics. And now whatever Schrödinger, not Dirac, Schrödinger, Heisenberg and Pauli, I mean, did, so I mean, we need to understand that, okay? And we'll use these linear vectors for that, okay? Good to go? Okay. So essentially we need to start with postulates, because see that time things they're trying different sort of things, and now there are processes you need to follow these things, okay, and try to understand and try to appreciate or try to comprehend that. First thing is that right now in a quantum mechanical particle we know that they're neither particle nor wave, so we need to define something, okay. So that Schrödinger came up with some idea. So we must have a wave function. You take it for granted. We'll see how to. You will see. I mean, just the way we had Newton's law. You never challenged Newton, right? He figured out long time back. Schrödinger, I mean, they figured this out long time back. We'll see how to use it. Okay. First thing is that you need to find, or for every single particle, we must have a wave function. So when it's a wave function, now there are two tracks. Okay, in some books one does it this way, other way. So you can have something like sine omega, sine kx plus sine, something like in wave form, or it is a bit sophisticated version. This wave vector is actually a linear vector. That's why we spent 10 minutes on linear vector. That's what you need to know. Just a linear vector. Okay or not? Do you understand this statement or not? Actually, both are same. Let me give you one example. In linear vector, what do you have? You have basis, right? If you don't remember anything, always think about 3D. If you understand 3D, you can see ND possibly. Okay, you have basis vectors and coefficients. These coefficients are discrete, right? Okay, and now I'm saying this vector is same as a wave. Do you agree or not? If you agree, you have to tell me agree. You note it in your head. You tell me why. Okay, let me just, okay, suppose I have a random wave. Okay, that random wave you can always decompose in Fourier series. So in terms of sine and cosine, series of sine and cosine with coefficients. This series of sine and coefficients constitute basis vectors for that. When you have waves, still you have basis vectors with coefficients. That's why they are same in my mind. One representation is a matrix form. You just take the whatever, column vector.
Like it is infinite dimension.
Huh? You can have infinity. Yes, let this be. Yes, let this be. You are saying that infinite number of coefficients, right?
Infinite like dimension.
Let it be. No, so here now it is time to explode and expand. Don't be afraid with infinity. Maybe the coefficients will drop down. You will forget after 7 or 8 coefficients. Okay? Now do you understand? Whatever physically wave like that, whenever I am drawing this wave or thinking about a real wave, that is same as this vector, linear vector. Different represent, same thing, two different representation. Okay or not? Okay? Yes. So this is the quantum mechanical wave function of wave vector. Okay? So what do we have there? You have coefficients. You need to understand the significance. So this is exactly what I mean. So if you, yeah, so this is exactly what I mean. So if you think about wave, so there are different bases for that, or also you can take a linear vector. But important thing, there are coefficients. Okay, what does it signify? Modulus of that is a probability for this state. Okay, yeah, if it hurts, I just help you. So in quantum mechanics, I already said the wave particle duality probability. Always these things come. Probability of what? Probability of different outcomes, right? Probability of different outcomes. So different, so that stems from here. Okay, suppose this wave, so suppose we have outcome or we get the state, okay, and this state will have probability with C1 square. There are probability, just one second, there are probabilities of different states. When we have a quantum mechanical wave function, there are different states, those are basis vectors, but they might have different probability. For example, if you have a wave, okay, normal wave, if you have the Fourier series, there are different coefficients, right, and they vary. So square of that, the wave function is defined such that square of that will be local probability or probability density. Question.
Probability of what?
Probability of finding particles here.
In 3D we have XYZ, so particles can follow that route only. In ND form we have multiple U1, U2, UI. So the particles can follow any wave. So probability of finding in that particular zone is that C1, C1, C2.
Mod C1, it is the way it is defined, mod Ci square is the probability associated to that. Okay? But the particle exists, right? Probability is fine. I understand there is a probability, but you must tell that particle exists in this universe. So total probability is 1. That means it should be normalized. So whenever you have a quantum mechanical wave function or wave vectors, you should be able to normalize it. Again, there are two channels. So if you follow this bracket notation, okay, meaning always think about the matrix multiplication. This coefficient should be 1. So this is a discrete. You have n number of rows, n number of columns, and you have this one, right? So C1 mod C1 squares mod C2 squares. Okay, there is a mistake. We must have modulus. I will correct that while posting. Okay, and also we can do it in this way.
Sigma 1 to infinite, from 1 to infinite.
Acha, here I just said, okay, I mean here I assume that it is up to n. You can give infinity. Okay, meaning the space, I mean the limits are from your interest. Okay, always you can run up to infinity, and after some point it will just die. Both are identical. One is a integral form, another is a summation form. Sum and integral both are same, right? Sum is a discrete function, right? 1 plus 2 plus 3. Integral is 1, 1.111, 1.112. It just when this 0.112 it changes to 0, right? That's the integration. These are two different forms. Are you getting or not? I'm telling you the reason is that sometimes it helps, sometimes that helps. Okay, you should know the both aspects. Is it okay? Okay, so we have this all probability and this and that. That means if you need, but you need to finally quantify something, right? The best way is to have mean. We call it the expectation value, expected value. When it is probabilistic, obviously expectation value and standard deviation appear. So these are the things we will quantify, and that's much better because whenever you are doing experiment, you measure something that is called observable. Whatever you are measuring, whatever you are really able to test, that's observable. And whenever you are testing something, you are bound to have errors or there will be standard deviation. So quantum mechanics actually captures that, which is fundamental, unlike classical mechanics or classical physics. Is it correct? I mean, is it okay? This is a postulate one. So you now understand just the wave function, okay? But still not getting, right? Okay, now, but we need to see more, okay? But by the way, is the first point clear? Clear? Okay? Okay. Next is finding this wave. Okay? It will not just fall from sky like heaven, right? That happens in many cases. People will say this came from heaven, believe it. But here, nothing like that happens. Okay? Yeah, it has to be substantiated, logically verified, experimentally proven. Okay, that's science. Okay, so then comes this Schrodinger, and he is famous for this Schrodinger equation. Okay, so these are called Schrodinger wave equation, just the way we have Newton's, and so this is the basis. Okay, he finally figured out doing back wave with different options. He came up with this solution that if you can solve this equation, whatever you will get, that is satisfy all the properties. So they just come one by one. Okay. So, but important thing you need to see, there are two parts. One is the time evolution. So this part, left hand side, has a time evolution or time dependent. And right hand side, what you have is a space, mostly space dependent. So here, this is the derivative with respect to space. This is, okay, x and t. Here, it is a potential. So this part is related to the energy. Okay, this part is related to energy. Okay. So still it is a bit complicated, right? The reason is in one side, it is a time derivative, and the side is the space derivative. And when we have stuff like that, it becomes complicated. Do you agree or not? Okay. So now the trick is the potential that we have. Okay, because you have to solve for it. So always you have kinetic energy and potential energy. You need the potential profile. For example, if it is a hydrogen atom problem, you need to know the Coulomb's potential. The stuff like that. Okay. So now most of the time, this potential is time independent. You can also make it time dependent, but we can simplify stuff. Potential is time independent. So this is V of x. If this is V of x, then it makes the life quite easy. Okay, because then what we can do, we can split this wave function into two parts. space dependent part, time dependent. We can split or isolate them. We will not be able to do if V was function of x and t. That you will do after putting in it, okay? So this is called separation of variables. This is very standard thing, very commonly practiced. Okay, so you can, yeah, so for the time being, let's assume V is only dependent on x. I've skipped some of the derivations here. But you can, so what people do, you try this solution. That generally works. So physicists or engineers always try something and see whether it works or not. If it works, they are happy. Okay, if it doesn't work, oh, I'll just try something else. Okay, that intuition is very important. In this course, you try to gain this intuition. Okay, my questions are in general very intuitive. Okay, try to understand, because most of the time I allow students to bring notes in exam. Okay, anyway, so here you have the space dependent part and time dependent part. Put this here and see what you get. So what will happen? I think I have skipped one. What will happen that, so this left hand part only becomes, only time dependent. It has a derivative, time dependent, time derivative. And right hand side, you will see that is given in my notes. I'll just show you. Okay, that right hand side is space derivative, and they are different forms. Right? If that happens, then they must be equals to some constant. So that means this guy equals to E and this guy equals to some constant E times this wave. Okay, finally from this you can get this time dependent part out. This is very simple. I just show you, I just include that in my notes. Okay, so here this is the time dependent part, very easy. So this is a time evolution. This is how function will evolve. The wave function will evolve as a function of time. It just adds a space, as a phase term. When you have e raised to some I omega t or something, it is like a phase term. The remaining part that you have is known as time independent Schrodinger equation. It is only space dependent. That's what we have. So there are two steps jumped actually in between. So from here, so that you can actually do is quite easy. Just consider V equals to V of x and try this trial solution. Put this back and then you will find this left hand side has time derivative, right hand side will have space derivative. Two different types of derivative, that means they must be equal to something. That something is a constant. Here it is energy and you solve for it. Okay, now this is easy. So because here you have certain things that you can solve for. There will be different cases that we will see, different type of potential profiles. Okay, for example, we'll see infinite potential well in the next class. We'll see potential barrier. There we'll see the tunneling phenomena, and also we'll work out for some cases like if you have periodic potential, because we have atoms. In the end, we don't want to go deeper in physics. Rather, we want to understand semiconductors, meaning periodically arranged atoms. So we want to know if we have periodically arranged atoms. If you have atoms, that means you have electrons, nucleus. That means you have potential, electrostatic potential. That means if you have periodic potential, okay, then what wave function do you get? And from that, what energies are allowed, what are not allowed? Meaning gradually you step into bands. Okay, now it is very simple. This Schrodinger equation was a bit complicated. You can simplify it. This is the bottom line. One is a time dependent part and another is a space dependent part. Okay, one is a time dependent part, another is a space dependent part. Okay, and then this time dependent part gives you the phase, trivial phase. There is something called non-trivial phase also exists. But anyway, we'll not get into that. And the space dependent part, from that you can get this wave function as a function of space, which is the most important thing. Because energy, and if you have space, reciprocal of that is k, you can get that E versus k sort of thing. Okay, now you know how to solve, what to do with this. Okay, but that's not everything, right? You had that operator, right? Finally, eventually, you have this wave function energy and momentum. Fine, okay. But we have that. But overall, our essence is that we want to do some measurement. We want to know the outcome, probabilistic outcome. Measurement meaning we need to do some operation. That's the third postulate. So we need to find eventually expectation value of an operator. Okay, we want to know the expectation value of an operator. Okay, and this is how, okay, actually there are many things to say. Actually, I could not include everything here. Okay, I just discuss it in next class, okay, because we should spend like 5-10 minutes, okay, and also I'll show you like in my notes what I have written, because this is the point actually. Okay, let me just give you a hint so that you can read a little bit. Whenever you are doing measurement, what kind of measurement are you doing? Are you measuring something for one single measurement, because that matters, or are you measuring in number of times simultaneously? What kind of measurement are you doing? You can do, yeah, when you're doing in number of, yes, one time, one or, okay, let's just discuss these two, okay. So, operator, so we have operator, okay, we have operator, and it will be operated on a wave vector. Okay, maybe I just write here, okay. So, we have this operator, n cross n, and then we have this wave vector. This wave vector we can define some coefficient and some basis vector, right? So as of this basis vector is not unique, we can also have a different choice, say d1, right? You remember in the crystal structure, the basis vectors can be different. We can also have other options, say m, say, okay. And now when we have this operator, this is n cross n, so we can have this eigenvector, eigenvalues, right? Okay, and correspondingly we can also have we must have eigenvectors. So I hope you understand. Right now we don't do it, just have a different notation. Do you understand? If you have understood this, that means you understand fundamental. Is it clear? That we have worked out, right? This afternoon. This is a matrix. We have these eigenvalues and eigenfunctions. Now look at here. There is a possibility that we can define these wave vectors. We can represent it with these eigenvectors, right? Right? Is it clear or not? We can represent also. So it might not be there here, it might not be the case here, but this is a possibility, right? We can have it. And all these coefficients are probability of occurrence. That means if you do one measurement, then probably you will measure, not probably, you will certainly measure one of these eigenvalues of this operator with the probability, and after this operation, this wave vector will be collapsed into this omega I. Very important. You understand it or not? Is it clear? Okay. So you know this matrix?
Yeah.
So there are n number of eigenvalues and eigenstates. We have a quantum mechanical vector or wave vector can be represented with the help of coefficient complex coefficient and basis vectors. Choice of basis vectors is not unique. We can have different set of basis vectors. But so here these basis vectors is same as the basis vectors of that operator we have. Okay. So then what you have? So when you do this, okay. Suppose this is V, we get into this, right? Then what happens? You will measure one of these eigenvalues. Suppose you measure once, then actually you measure one of the eigenvalues. That means the eigenvalue of this matrix is the outcome. This is very important point. This eigenvalue of this matrix is the outcome. If you measure it one time, you don't know. You can measure any of them. There are n number of eigenvalues. Maybe you will measure lambda I. You can measure lambda 1. Maybe you will measure lambda 1. You will measure lambda 2. You will measure lambda 3. You will measure lambda 4. You can measure one of them. But if you simultaneously do it 10 lakhs times.
So for the same or for different?
What do you mean by here? Every single word matters. What do you mean by same or different?
For the same lambda or for different lambdas, like different eigenvalues.
Okay, let me just repeat what I said. Suppose I am doing one measurement. I am meaning you on same particle. Suppose you measure. You will measure one of the eigenvalues, say lambda 1. He can measure lambda 2. He can measure lambda 3. But whenever if you do one measurement, you will get one of the values. That's the essence. Okay? And after the measurement, you will not have this wave vector. It will be collapsed to this eigenstate. But suppose n millions of you are measuring, then maybe 20% of you will measure lambda 1. 30% of you will measure lambda 2. 3% of you will measure lambda 3. There is a probability. That probability is associated with this one. This one. That means if you do simultaneous measurement infinite number of times, okay, or million times, what do you get? Finally, I don't want to listen what you get individually, tell me the average. You get the average or you get the expectation value. So that is nothing. So this is 1. Okay, now this is n number of measurements. Okay, the average value. The average value is, okay, so this is the probability multiplied by lambda. Sum over it. Lambda 1 mod d1 square, lambda 2 mod d2 square. Right? That is what expectation value is. Right? This is how you do the averaging. Right? What is the average of these numbers? 1, 2, 3, and 4. What is the 5? What is the average of it? You do which one do you do? Do you do this taken method? You do this method? I am asking. Is this a method? Or you do this one?
1 by 5 and
Right. 1 by 5, 1, 1 by 5, 2, 1 by 5, 3, 1 by 5, 4, 1 by 5, 5. Or you do this one. There is a subtle difference. You learn this one, I learned this one. But it works because all of them are equiprobable. So their distribution is equal. So this probability is same. That's why you take it outside. This is exactly what we're doing. We're not doing any fancy or new stuff. Probability times the outcome is the expectation value, is the mean. Okay? Now, is this clear? So that's the average one. Okay? Average outcome. And see, this term. Okay, square of that, right? Square of that with lambda. So we can just very briefly, maybe 1 minute, square of that. Okay, so previously you have seen square of that somewhere, right? Or maybe I can also make it, write it in a fancy way. So maybe, do you agree? This, is it okay? So now you can relate. So this guy is nothing but this is, okay? And then we have lambda and we have, right? Right? Do you agree? So I'm just expanding this in terms of this coefficient. So this guy is nothing but this, right? Complex conjugate of this guy is nothing but this, and in between I said that we can diagonalize it if this is on that basis. Okay, this is nothing but, sorry, omega. Now if I put them together nicely, what you have, we have psi omega psi. Okay, that's what we have here. Okay, anyway, I could not add it here, but I explained. This is psi omega psi in bracket notation, or this is over integral form. Okay, I think let's just stop here. Okay, yeah, we have small things remaining that